So this is our next to last class. So we're going to try and run through as much about routing as we can. I hope you all got the email. The final project has been posted to the website. I have one additional schematic that I'll give you guys that will show how to hook up with Compact Flash already, so that'll make your lives a lot easier rather than having to dig up data sheets for that. So are there any questions about the final project so far if you've taken a look, or problems with getting Allegro working on your machines or anything like that? Yeah.
Other than Digicam mouse, do you recommend?
Sources for parts. So I'll put up a slide or two probably tomorrow that'll have vendors for parts. Because unfortunately I don't think we're going to have time to run through a whole bunch of them here. So any other questions? Yeah. So the question is, do you need to put the ISP connector on? And I would highly recommend it, because if you don't, it's not going to be too useful. It's what? But if you have a compact design and you can't program it, what's the point? All right, so the question was, guys, if you guys can keep it down a little bit. I know it's like Friday almost. So the question was, do you need to put an ISP connector on your board? And I would suggest so, because if you don't, you can't program it. And if you can't program it, it's not fully functional. So there are a lot of support pieces that you're going to need on your boards that may not be explicitly listed in the project that you'll have to add. Yeah?
You said you give points for compactness.
Yes.
Can you suggest any way to make it compact other than just cramming things close together, like dragging?
So the question is, are there any tricks you can do to make things more compact other than just cramming stuff together? And you're stuck basically cramming stuff as tight as you can and still route it. So that's what's really going to limit your density, is your ability to route all of these air wires. Yeah?
You say you want the unit price that you're saying.
Yes.
If we buy 10 of them, can we take the unit price for 10?
All right, so the question is about unit price, and if you can only buy the part in quantity 10, you can put the part, like some of the resistors. All right, if you're using 10 of them, or if you're using the certain amount, you can take the price break for that. Otherwise, you have to do for the per component. So any other questions? So I would definitely recommend starting early. So Tim and I will have our regular office hours through Wednesday next week. And then after that, I think it's like dead week before finals and all of that. But we'll have extra office hours that we can work out next class to help you guys out. But if you're not ready to do your layout by early to middle of next week, you're going to be running into problems because layout takes time. So it's a challenging project, but I think it's doable. And I think it'll be a lot of fun at the very end to have your own PC board. So any other last questions on this? All right, so let's get back into layout. So this is where we left off last class. We had exported our net list inside of Design Entry CIS or Capture CIS. And then we started a new layout project. We imported that net list. We picked all of the footprints for the parts, and this is kind of where we were. So again, these are the actual footprints. And then all of the yellow parts are air wires between things. And so just a reminder that the typical I for zooming in, O for zooming out, and C for centering still works here. So that's how we're going to be maneuvering around today. Now, one other thing you'll notice is there's this dotted line, kind of like a target in the center of the screen. So this is for something called Design Rules Check. So that's DRC, and the button is right up here. And what Layout Plus will do is it will check your design rules. So it'll check your track-to-track spacing and track widths and things like that inside of just this dotted box when online DRC is on. The problem is that if you start moving things around, and I just click on it to grab it and then let go, and then you can move it wherever and click again, if you put it somewhere that's not fully within the box, it barks at you with this error saying unable to verify or clear design rule check. So a lot of times you have to be careful about having this box on, because it'll error out on things that aren't really problems. Like if I try and move it out of the box, it won't let you. So to start with, at least for component placing, we're going to turn off the design rule check. So now the box goes away and you can freely move things anywhere you want and it won't get mad at you. So the very first step to do is to actually place all of these components on your board. Now remember that this little target down here is the origin. And if you look at the very bottom left of your screen, down in this area, you'll see that there are coordinates, and that's in mils, and that's where your cursor currently is. And so you'll notice that they're jumping by hundreds right now. And a lot of times that's not going to be very fine if you're trying to put, let's say, 2 of these capacitors right next to each other. You can't necessarily line it up exactly the way you want. So you can alter your global spacing, which are these grids, like snap 2 grids, by going up to the options menu and then clicking on system settings. It's not very intuitive, but that's where it is. And here you have your grids, so you can display a visible grid if you want visual clues for how you're lining things up. There's a place grid, which is how you're actually placing the components. So that's what we're doing right now. When you start routing traces, there's the routing grid. And so this is going to be means that basically each of your traces are going to be on 25 mil increments. So if you looked at the project, I think you have 8 mil trace and space tolerances. So making this grid 25 is pretty bad. So we'll make it like 1 for routing. The place grid, it's nice to help you line up components if it's something somewhat large, but you still want to be able to get things close. So we'll just make it like 10 to start with. You can display your units in any type of units you want, but remember that we are going to be working in mils, and most of the board houses here in the U.S. work in mils. And then you have rotational increments. So if you want to be able to rotate parts at 45s instead of just 90s, you can change that. So these are the grids which will help you be able to place components tighter together. So questions about these grids? Yeah. What's the what? So the routing grid is the grid that is used when you're actually routing traces. So if you have this routing grid at 25, then that means that endpoints of your traces can only be at 0, 25 mil, 50 mil, 75 mil, 100 mil. And if you have fine-pitched components, like, for example, this an SSOP package or TQFP like your at Mega is, 25 mils won't be enough to actually be able to get to select the pin that you care about. So drop your routing grid down when you're doing small stuff. Yeah?
If you press Alt, does it override your grid and let you go wherever?
The question is, if you press Alt, does it override the grid? I don't think it does. We can try, but I don't think it does. Yeah?
How advisable is it to have non-90-degree increments and rotate
So
45 or 30 or something?
Yeah, so the question is, how advisable is it not to have 90-degree rotation increments? So you're welcome to do whatever you want. In general, so the fabrication complexity is the same. So when you lay this out, basically they're going to either laser cut or lithograph or do some process to make all of the copper. So any designs of copper are equally trivial to make as long as you have a square board. If you don't have a square outer edge of the board, it gets a bit more expensive. So you're welcome to rotate components. On typical productions, you only see things at 90s typically. If you have some really high density parts, sometimes they'll be rotated at 45 just to keep things like off the grid, so to speak. But typically things stay at 90. But again, if you want to make a pretty looking board for some reason, you're more than welcome to. So any other questions here? Okay, so we decreased our grid size, and now you'll notice that we can move this quite a bit more finely. So to start with, let's just go ahead and lay out where all of our components are going to go. So remember that this is 0 right here. This is our origin, and that you want your circuit board to be in positive increments. So you want your board to be up in this quadrant, right? Don't build things in the other directions. It'll sometimes confuse certain board houses. Yeah. Yeah. There's nothing wrong with doing it, but a lot of times the CAM engineers will get cranky. Now you'll notice that this is that DB25 connector we have, and that the actual pads are back here. So this is a through-hole part. They're round. But the plug actually extends out the front. And if you look on your board, the plug does extend out past the board. Otherwise, the housing of the connector you're plugging in would jam against the circuit board as you're trying to plug it in. So a lot of times you'll put your board edge right here, if that makes sense. So if you're looking at things like your headphone jack, for example, your headphone jack probably is going to have a small round piece that extends past the front of the board. And you want that to extend out because it allows a thickness for like a housing or a case or something like that to go on. So you're not like pushing this whole connector off, but if you look carefully at your board, there's the actual D connector, and that D connector is this part right here. And everything from here back stays on the board. So is that kind of clear? Yeah.
how are they? How are they on the board? Are they flat or?
So these are through-hole pins.
Oh,
So these are holes that are drilled in.
okay. So and then from there we draw the traces.
And from here you draw the traces, which we'll get into. So we're going to take a look at the pad stack and all of the layers we have once we get these components kind of laid out. Yeah.
When you say DB9 pin, how is the bus actually? How is the connector actually? Is it like normal RS-232 connector, or is that a bus that slides into a slot?
So this is a DB9 just like on the development board. So this part is something that we picked out of the library because it's standard. But for example, like your headphone jack does not have a footprint in the library, so you'll have to create your own footprint for it. So these are just parts that you actually can buy. Luckily for us, the DB connectors are very standardized. So this will work with a lot of manufacturers' DB connectors. All right, so what we're going to do is we're just quickly going to place a couple of these parts. You can select multiple parts by dragging a window around something and then clicking and dragging around. Just be careful because like right now, I've clicked, I've dragged, I've let go, the parts are placed, but if I click over here and start moving, it moves the parts with you. So if you click and drag something and you don't see anything happening on your screen, it could be, for example, if you're zoomed in like right here, and I click and drag, I'm not moving this connector, but when you zoom back out, you'll notice that I actually moved these capacitors. So it locks components in kind of a weird way, so just be aware of that. So what we're going to do is we're going to put one of these connectors on this edge of the board. We're going to put another connector on the other edge. We're going to put the chip somewhere in the middle. Now you'll notice that you can rotate the components. And we also have a top and a bottom layer where we can actually place components. So if you look up here, these are our layers. So this menu selects the layers. And top is the top of your board. BOT is the bottom of your board. So these are the only places where you can place components. And we'll look at the rest of the layers here in just a few minutes. So if we click on bottom, you'll notice that the part turned from green to red. So let's go back to top. So you see the pads are green right now on this line driver. If I click again, click bottom, they turn red. Because red is the color for the bottom layer. So that's the color right here. Which means we're now placing this component on the bottom of the board. Now that also kind of mirrors it from your perspective because you're still looking at the board from the top view. So when you're looking at a sheet of paper from the top, the things that are written on the back are mirrored. Does that make sense? So don't forget that if you have lettering that's on the back of your board, for example, which we'll talk about later, and you make the lettering look correct, when you fab your boards, it'll actually be mirrored. So everything on the back layer is backwards of the way it'll appear in reality once you fabricate it, because you have this fixed top view. So we're going to just leave this on the top layer for now. We're going to make this a simple board. Now as you rotate around, you'll see that these air wires are moving, and that's showing where the actual connectivity is. So if I put the chip down like this, you'll notice, for example, on both sides, there's a lot of kind of crisscrossing. It looks like an X. And that we're going to be routing actual physical signals. So if you do that, it's going to be kind of complicated to get all of the signals across. You're going to have to go up and down between layers a whole bunch. Whereas if we put it this way, it's a lot more straight. There's only a couple wires that are crossed. So when you have large parts, like your processor, you'll want to put it down and rotate it around and see which way looks the cleanest. And you also can flip layers and put it on the front or the back, because when that mirrors everything, that also kind of changes the pin ordering, at least from the perspective of the air wires. So you'll be able to rotate it around all the way around on the front of the board and all the way around on the back of the board, and that'll change the way these air wires are coming out. Now, you don't have to route in the exact direction of these air wires. For example, if you're trying to go to this right connector, you can come out on the left side of the chip and go up, down, left, right, all around, and then back into the connector if you need to. But the air wires will just give you a general idea of kind of the density and direction of traces. Question?
Yeah, I'm curious. You said you wanted to keep it simple, so you're going to put it on the same side.
Yeah.
Since those are through the hole pins, wouldn't it be easier to put them on opposite sides?
All right, so the question is, I said I'm trying to keep this easy, so we're putting this on the top. But since these connectors are through hole, isn't it easier to put the component on the bottom? Well, remember that all of your component holes and vias are plated all the way through. And they have that annular ring that we talked about last class on every layer. So you actually can get to the signals off of these connectors. So if we zoom in here, you can get to any one of these pads on the top layer. So I just press 1 to get to the top layer. or on the bottom layer. So you don't need vias to change layers. So through-hole parts are available in every layer automatically. Surface mount things are only available in the top or bottom depending upon where you put it, because they just have pads that sit on the top and no holes that go through.
So
Yeah.
what's the perspective mean the bottom that comes, so we're looking from the top at this point?
All right, so the question is, what's the perspective for the bottom compared to what we're doing right now? So right now, we're always looking from the top. So what we see in normal view in green is the top layer. And that's the way it would look if you're looking at the top of the circuit board. Everything else is still from that top perspective. So the bottom layer, you're looking at through the board onto the bottom. So the bottom layer is basically mirrored. So you can think about this as being a sheet of paper, and if you hold it up to a light, you're looking at the top, but everything on the back is backwards.
So if we want to print something at the back, it should be right.
Yeah, so if you want your text to appear properly, and you write text on the back, make sure you mirror it. Otherwise, it turns out mirrored when you fabricate it. Yeah?
So is there no way to say, give me bottom view now?
So the question is there a way to give you the bottom view? I haven't ever seen one. I don't think there is. There may be hidden somewhere with a hidden key command. Because there are lots of key shortcuts that are not shown on menus, but I'm not aware of it. So other questions so far? Okay, so again, you click on an item, it locks it to your cursor, you can move wherever you want, you click again to drop it. Now, right now you can tell that these two connectors aren't quite level, so there's a way that you can actually turn on crosshairs to see where things are, and the shortcut for that is the plus sign on your keypad. Now, I haven't been able to find that anywhere on these menus. So this is one of those you just have to magically know what these shortcuts are. So I'm trying to help you guys out here. If you hit plus, you get crosshairs everywhere you go. On some versions, if you hit plus and now we center and then recenter, you'll notice it's drawing all these lines everywhere and making a mess. And remember that you can hit F5 to redraw your screen, and all those lines go away. That's what you get in a really expensive piece of software. But it's still sometimes useful to have these crosshairs, especially when you're lining things up. So we still have all these capacitors, and we have this power connector. So we can grab the power connector and place it wherever we please. We can put these capacitors nearby. So again, if you select on a component, let's say C2 right here, if we go back to our capture or design entry, it will show that capacitor highlighted automatically. So if you have multiple monitors, this is really easy to do, where you can have your schematic on one side and your actual layout on the other. And this will kind of help clue you into where that component goes. So again, you want to put most of the capacitors as close as you can next to where they go on the chip. And don't worry too much about the lettering at this point. So these letterings get all over the place and make a big mess, and we'll clean them up at a later stage. Now, if you place your component like this, remember that you have these crossed air wires. And that means when you're routing a track, you'll have to make this track go this way and then this one come out and around. Whereas if you just rotate this 180 degrees, now the wires can go directly in. So placement is important. Take your time with placement. So I'm just going to quickly place the remaining ones of these guys. Now you'll notice right now that this capacitor is hooked up to another capacitor into one pin on the board. And if we go back, we select the capacitor and then go back to our design, you'll see that this one eventually goes to ground. And there's another one that goes to VCC. So that's not too terribly crazy. Yeah, question.
Have you made it so that your grid size doesn't let you place components too close together? As in, so you said that you can only place components like 10 mils or
So the grid spacing is, if you look at when I move the mouse right here, the component jumps by an increment of whatever the grid spacing is. So I still can make illegal placements like that. So the grid spacing there does not help with design rules, unfortunately.
But in a sense, you know that if visually they're not overlapping and the grid spacing is such that it's larger than...
Correct. Yeah. So if you know that your grid spacing is larger than your minimum, and you can see that they're physically not overlapped, then you're fairly assured that it's not going to actually be illegally placed. All right, so at this point, we have all of our components laid down. But we still have this mess of air wires to route, which gets exciting. So we're going to make this a 4-layer board, and this really could be a 1-layer board, but we're going to do this just to show you all how to use the different layers. But there are a few things we want to take a look at first. So remember that we have design rules. We have a minimum trace width, we have minimum trace-to-trace separations that we have to deal with, and we also have only certain layers we want to use. So to start with, let's take care of the DRC, the design rule checks. So if we go to our options menu and then go to global spacing, we're presented with a list that shows all of the layers on the left-hand side and then the minimum separations on all of these columns. So for example, you can have track to track, track to via, track to pad. And for different vendors, they may care about track to track versus a track to pad. For the vendor we're using, we're just going to assume that a pad and a track and a via and everything like that is basically the same. Copper is copper for us. So you'll notice right now everything defaults to 12 mil. So we can get away with 8. So you can either double click on each one and type 8 and put it back, or you can click and drag across it, select them all, hit enter, and then just enter the values. So since they're the same all across, we're going to do that. And we now have 8 mil everywhere for our spacings. Everybody okay with this? Yeah. So if you either double click on an item, you'll get the menu for just that one cell, or you can drag to select multiple cells wherever you want the cell selected, and then hit enter. Oh, this dialog is from Options, Global Spacing. So where do we get this spacing information from? It's given to you by the board house. So in your assignment, there's one subsection that has all the spacing tolerances and annular rings and things like that. Any other questions on this part? Yeah.
What is these spacings do exactly?
All right, so the question is, what are these spacings for? So these spacings are just for your design rule check. So the program has a built-in design rule checker, a DRC, that'll check through your board and make sure you don't violate these spacings. Also, if you have the online DRC selected, so remember if we click up here, we get this little box, and it's much smaller now because we decreased our route spacing, which we'll talk about in a minute. Now everything that you route in here, it'll only allow you to route things that fall within those DRCs. And I'll give you an example of that in a minute. Yeah. So the box stays centered on your screen, and the only way to move it around is to move your view by moving your mouse and hitting C. The question is, can you make this box larger? So the box size for the auto DRC is basically related to a number of points that it's checking for you. So remember when we set our spacings up here under Options, System Settings, and then our grid. If our route grid is much larger, meaning less granularity in your routing, so for example 5, the box should have gotten larger. Yeah, now it's quite a bit larger. So the box size has to do with the number of points inside of it. And that the number of points inside are based upon the grids. The problem is that when you're routing some of these small things, you're going to need a pretty small grid. So you may find DRC, the auto DRC, the online DRC, to be constraining, because you can't route anything past the border of that design rule box. Yeah. All right, so the drill layer is the actual holes that you make on your board. So let's actually go ahead and cover that right now. So if we go to the Tools menu, we select Layer and then Select from Spreadsheet. So this Select versus Select from Spreadsheet is pretty common across the Layout Plus tool. So you have a lot of different options where you can select it either directly off of your actual layout or from a spreadsheet. The spreadsheet generally is much easier to work with. So again, tool, layer, select from spreadsheet. And now it shows the list of all of the layers we have. And there are quite a few of them. So the drill layer is a layer that's used for the CNC, the computer numerically controlled driller that actually drills holes on the board during fabrication. So the only information on the drill layer are holes, basically for vias or component holes or mounting holes or what have you. So if we look at the rest of the layers, we have a top and bottom layer. So this is the top and the bottom of the board as expected. And we have ground and power. So these are plane layers. You'll notice they're indicated as that under the layer type. So that means that these layers are going to be predominantly copper, and you're just going to etch basically where you don't want copper. So remember that your ground and power planes are basically just all copper with ground, and then if you have a via, for example, that's not connected to the plane layer, then you're going to leave a little space so it's not electrically connected. But otherwise, these are flooded completely with copper. Your routing layers, which are up here, the top and bottom, as well as inner 1 and inner 2 by default, is where you actually route your copper traces. So by default, there's nothing on that layer, and as you begin routing, you're routing actual positive copper. Is the distinction there clear? Okay. So for our board, we're just going to be using a top and bottom and a ground and power. Now again, for this board is trivial. You don't really need a 4-layer board for this. You can probably do it on 1 layer instead of 2. But just for demonstration on what we're going to be doing for this project, we're going to select 4. So right now you can see top and bottom are set as routing, which is what we want. Ground and power are set as plane, because we want those to be plane layers. But we also have inner 1 and inner 2 selected. So these are just additional layers for routing if you have a complex board. So we're going to click and drag, select both of these, and you can either right-click and go to Properties, or you can just type Enter to bring up a similar box like you have before. And we're going to say that this is unused routing, which basically means we're not using it. Your other options, you can have a routing layer. Again, this is where you draw positive copper. You can have a plane layer, which is where you draw negative copper. In other words, the whole layer is copper except for where you draw. Documentation is just used for your own documentation if you're assembling the board or want to give a drawing to someone else. Jumpers are pretty uncommon, but jumpers would be if you have external, like on the top of the board, jumpers. And the drill layer, again, is for all of your drill bits, holes, routing of the board edges, things like that. So we're going to leave these as unused routing. So we have 2 routing layers and 2 plane layers now. We also have documentation. So let's look at these other layers down towards the bottom. So SM top and SM bottom is the solder mask top and bottom. So in your boards, remember the solder mask is the green. It basically protects the traces from corrosion. It protects you from shorting things. And it also protects the traces from wicking away the solder from your pads as you're heating them up. So your solder mask will cover everything except for pads, because you want them covered. Below that, we have SP top and bottom. So this is solder paste, and this is used for a type of soldering that you may be able to do. So industrially, things are soldered with paste, which is kind of like a gel that you put on the boards. If you create these layers, the board house can actually fabricate a stencil for you, and you can do solder paste on your own. So if you came at the beginning of the quarter while I was assembling these boards, we actually did use solder paste. And the solder paste stencil, the metal stencil, was generated directly from these layers. For this project, you're not required to do that. It's basically no effort to do it as long as your footprints are correct. So we're going to leave these enabled. You'll notice we have silkscreen top and silkscreen bottom. That's SS top and SS bottom. So again, this is your legend. This is where you can write things, you can draw things, you can label your parts with designators. You can also put free text to indicate, for example, what a port function is, or to put your names on it or a copyright or something like that. Below that, we have assembly top and bottom. So this is typically used by part pick-and-place robots to assemble your board. We don't care about this. There's a drill drawing, and there's also a drill for the NC. These two are fairly related. It just has to do with different fab house processing types. Fab drawing, very similar to these above two. The fab drawing is also where your board outline will typically go. But that's not something that you have to do. And then notes are where you can leave comments either to yourself or to someone who's stuffing your board or whoever. So these are the layers. Again, the ones that we really care about right now are top and bottom and ground and power. So any question on this layer rundown? Yeah?
Do you have to about the solder mask layers, or are those generally automatic?
All right, so the question is, do you have to worry about the solder mask layer, or are they automagic? So solder mask is a negative layer, so it will always be covered except for where you draw things. Now, as long as you design your footprints properly, you'll draw an opening over your pads and the solder mask layer. And as long as you do that, you don't have to do anything else in your routing. Now, there may be instances or cases where you do not want solder mask over some of your traces. So, for example, in some of the boards that I had in the lab that you all may have seen, there were large blocks that had no solder mask on the back because they were high-power traces, and I wanted to be able to put solder on top of those traces to beef them up for higher current. So you can draw obstacles, which we'll talk about next class, that will open up the solder mask. Otherwise, it's everywhere except the pads. Yeah?
What kind of things do you write in the notes?
Question is, what kind of things do you write in the notes area? Well, for example, if you had a jumper and you don't want it stuffed, you could say, do not stuff this jumper. Or if you're coming back after you fabbed your board and you noticed a problem, you can comment on the problem there. It's basically any type of generic notes you want. We rarely use the notes layer. Yeah?
Can we delete layers that we don't need?
So the question is, can you delete layers that you don't need? You can, but I don't think it actually deletes them from here. You can add new layers, but deleting them is kind of hard to do. We just leave them set as unused, and they'll disappear. Yeah?
What if you have more than one power supply, like 320 and 5? So which one is the power player?
That's a good question. So when this says power, what power is it? So you have to specify which power is hooked up to this plane layer. Now, if you want to have islands of different power supplies, so for example, you have half of your board physically that's 3, and half that's 5, and it's physically separated, then you probably would want to make it a routing layer, and you can draw a copper pore, which is an area that you specify as filled with copper across those two areas. The other option is that on some, advanced boards, you're going to have multiple power layers, and you can rename this inner one to like power 3 and power 5. These names are pretty much arbitrary.
In those cases, do it actually take care of separating those power, the planes by a ground plane or something? Do you have multiple ground planes too?
So typically you just have one ground plane. If you need more ground planes for, for shielding or something like that, you can specify additional ground planes. And then when you actually have your board fabricated, you have to check with your board house to indicate the fabrication order. Otherwise, I think they kind of arbitrarily place your layers. So other questions on these layers? So one other thing I'd like to point out here is the column that says the layer hotkey. So if we're on the top, you can just press the number 1 and it'll jump to the top layer. 2 will jump to the bottom layer. 3 will jump to ground. 4 will jump to power. So these will become second nature, and it's very important when you're actually routing connections. Okay. So again, if we look up here now, there's no longer an inner 1 and inner 2 layer. They disappeared because we set them as unused routing. So we now have top, bottom, ground, and power. Another option that we have to deal with are the nets. So if we go to Tool, Nets, and then select from Spreadsheet, this will show, and we can hit Cancel because we're not searching. This will show a list of all of the nets that we have in the schematic. And this is a simple board, so there's not a whole lot of nets. And the ones that we've named have nice names, and the ones we didn't name were assigned these random N and then a number. Now you notice that you can also select the color. So if we go back and look at our layout, all of these are yellow right now. Well, if we want to indicate, for example, that ground is going to be a special case, we can right-click on the ground row, go to Change Color, and maybe make ground green. And we can do the same thing with VCC, and this is just for your own use. This is just to help you figure out what's going on.
Are there industry standards?
There are not industry standards as far as AirNet colors. It doesn't matter. I typically use the same color for the AirNets as I would for wiring. So red is 5, and orange is 12, and purple is 3.3 or something like that. But VCC here is actually 3.3, so it doesn't matter. So we can change the AirWire color. So now you'll notice there's some red and green down here, and green's going this way. So it's very clear which nets are ground and power, because those are special cases for us. You can also enable or disable certain nets by just clicking on the column here. So double clicking, and you can actually disable routing if, for example, you don't want to route that net for some particular reason. You can also change the width, so the minimum width of the trace, the standard width of the trace, and the maximum width. So these minimum and maximums are used by DRC to verify that you have the minimum and maximums. The common is what it will automatically start up using. So we're just going to select all of them. We'll right click and go to properties. And our minimum width is 8 because that's what we're specified in our tolerances. Our maximum width we're not really going to care about, and we'll start with all the traces being 8 mils wide.
What happens if you leave that? Oh, 12.
Yeah, if you leave it defaulted, it just doesn't change it. So we actually can come back here and say, we can leave these alone because they're already 8. We can set the maximum width to something huge like 100. That way it won't give us errors during DRC. So the other thing we can do is that, remember that our ground and power are special cases. So if we click on the ground row and go to properties, there's also a net layers button. So if we click on the net layers, it'll show which layers you're allowed to route this trace on, and we're going to allow you to have ground routing on the top and bottom. But it'll also allow you to select a plane layer and say that that plane layer is attached to the net. So this is our ground net, and we want the ground plane to be all ground. So we select the checkbox. So at this point, grounds are connected to the ground layer. We're going to do the same thing with VCC, except we're going to put VCC on the power plane. So at this point, we've pretty much set up everything we need for routing. There's one more option I'd like to introduce you all to. So we talked about the pad stack briefly and defined it the other day. So if we go to Tools and Pad Stack, and again we'll select from a spreadsheet, and we don't need to search. The pad stack for the global layout is basically going to specify all the pads for vias. And it may also have some pads for all the different footprints that you have. But what we're going to care about is via 1. So via 1 is the standard via that we use. Now remember that vias are holes that you use to change layers on your board. So underneath via 1, which is the name, and you can create new layers by right-clicking and saying new, but we don't need a new pad stack. We're just going to modify via 1. These are all of the layers that you have available to you. And then next to that, on each layer, you can specify the shape of that pad, the pad width, the pad height, and then these offsets. And we don't really care about the offsets. Leave the offsets to 0. So for us right now, if we go down to the drill layer, you'll notice that our vias are 28 mils in diameter. So those are pretty big vias. So if you start routing your board right now, it's going to get kind of cluttered. And according to the tolerances that I gave you all, you guys can use down to a 10 mil finished via hole or 14 mil diameter for a component hole. So we're going to select all of these. And remember that the drill drawing, the drill, the fab drawing, and the notes are basically going to all be the same. And you can tell that because it's also the way that they default to. So then we'll right-click and go to Properties. You'll notice that it's going to gray out options that you haven't selected. So we only selected the pad width and pad height. We didn't select the shape or anything like that. And we're going to change the drill to be a 10 mil drill, for example. So this is the smallest you can do at the current board house without having to pay more money. So now this jumps down to 10. So we now have a 10 mil diameter drill hole for the via. But we still have huge pads. So if we go back and look at your tolerances, you'll realize that you have to have a minimum annular ring of, I believe it was 5 mil diameter. So we're going to decrease this for the top and bottom layer. And we have a 10 mil drill, which means that at this point, the pad, which is the size of the drill plus the annular ring, has to be at least what? 15. It's going to be the diameter of the hole plus the annular ring. So we'll create these as being 15. And we'll do that on all of our inner layers as well. Excuse me? We're not using these inner layers, but it's a good idea to keep all of your layers consistent. So that way if later on in this project you add another layer, you don't have to go back and modify all of these again.
Wouldn't that be 20?
It's diameter.
Both the sides.
It depends on the specification. So right now we're going to assume that you have to have a 5 mil diameter increase for the annular ring, which means 2.5 on the radius. So this is a pretty small annular ring. Now you notice that the solder mask is larger than the actual pad. So there's something called solder mask swell. And so I believe that that's about 5 mil as well. So the solder mask swell is basically how much it's going to swell during the fabrication process and potentially encroach on your pad. So to keep your pads clean, and again, check your tolerances for what value you're supposed to be using, but we'll assume it's 5 millimeters on the diameter dimension, or 5 mils on the diameter dimension. So if we have a 15 mil pad on the top and bottom, then we should have a 20 mil solder mask. Does that make sense? Remember that solder mask is a negative. So anywhere where you have a pad of solder mask is where solder mask will not be deposited. So we'll set these both as 20. You'll also notice that for the ground and power, there were larger annular rings, larger pads. And that's typically because you're carrying higher current on these plane layers. Fabrication processes, it doesn't really matter. But you want to make these generally a bit larger just to give you some more current handling capacity. We don't really care too much, but we'll just make them a solid 5 mils on each side as opposed to just 5 mils in diameter. So at this point, we've modified our vias where our vias are now much, much smaller. So any questions in this process or on what any of these values mean? Yeah?
When would you ever use the X and Y offset?
So when do you use the X and Y offset? You can use it depending upon the parts place machine that you're using or how you reference your dimensions to basically place the center of the pad, the pseudo center of the pad at the corner of the pad as opposed to in the center. So it's just a way of moving the physical pad from the reference location of that pad. So if you have baseline dimensioning, you might want to have the pad be to the upper right. Yeah?
Now that you've changed your ground and power to 20, shouldn't your solder mask top and bottom be 25?
So the question is, since I changed the ground and power to 20, shouldn't the solder mask be 25 now? So the solder mask only goes on the top and the bottom of your boards. There's no solder mask internally. So the solder mask is related directly to the actual top and bottom. Now, this is a through hole, so you'll notice that for the solder paste and the silk screen, we left them as 0. So that means that we want to go ahead and not have any solder paste over a via, because you're not soldering to vias, and that you don't want to have any legends or anything like that printed on top of the via. Also, the assembly has no entry over the vias because there's no assembly instructions when you're assembling a via. So any other questions? Yeah.
So if you have a bottom layer, but you don't want to place any parts on your bottom layer, is the through hole going to show up on the bottom layer, and is there not going to be any solder mask on it because of all these settings?
Okay, so the question is, if you have a bottom layer, but you're not using it for any components, will these vias still show up all the way through? So traditional vias go all the way through your board. They're plated on every layer, so they will show up on the bottom. And you still will have your solder mask cleared around that via.
So then you could touch something to that via.
Correct, so you can touch something to this via. It's possible to not have your solder mask exposed around a via, to just basically coat the whole thing, but some fab houses will get upset with you for doing that. Now, it is possible to make vias that only go between specific layers and not all the way through, and they're called either blind vias or buried vias. So, for example, if you go between ground and power planes, but nowhere else, that's a buried via, as well as blind. So, those cost a lot more because it's harder to assemble your boards when you have them. So, for us, vias go all the way through. So, any other questions on this?
Is it like that on our dev boards as well?
So your dev boards do go all the way through, yes. And there is solder mask relief around it. So remember that all these values that you're picking here come from your tolerances. So you decide the hole size you want for your via. So if you're carrying more current, you may want a larger via, or you may just want more of the vias. And then from this drill, you have to pick the top and bottom to at least be what your annular ring is, and you can make these quite a bit larger. If you take a look at your design, these are going to be tiny, tiny annular rings. You specify the insides to, again, help out with your current handling capacity. And your solder mask has to account for the solder mask swell around the pad on the top and bottom. So most of your tolerances come into play just on this one sheet. All right, so at this point we've covered the grid spacings, we've covered how you set up your design rule checks, the pad stack, which we're looking at right now, and the different layers on your board. So, as well as the net selection, changing net colors, changing which planes are connected to nets. So any questions on that part so far? Okay. So we may have this layout right now, and you're kind of curious, how hard is this going to be to route, relatively speaking? So there's something called a density graph. So if you go to View and then Density Graph, and this is just the level of detail it gives you. On some boards it may take a while to run. If we do a fine density graph, you'll see, for example, that there's a lot of connections that are crossing over around the connectors, and quite a few on the pins, but in general this isn't going to be a fairly hard board to route. If you have like a spot where there are no components and tons of red, it means there are a lot of traces crossing over each other, and things are going to get tricky. So this is one tool you have available to kind of take a look at how you've placed your components and see how bad things are going to be. You also have the kind of 2D density graph. It says there's a lot around the connectors on these edges, and there's a lot around the IC in the middle, and not a whole lot in between. Not a big surprise there. So this option is in the View Density Graph, and then pick your level. If you do a coarse one, it just shows a lot less detail. If you want to get back to your design and it's disappeared, you can either click on it down here, or you can go to View and Design, and it'll pop back up. So at this point, we're pretty much ready to actually start routing. Yeah, question?
Is it arbitrary how far your DP9 connectors are from your chip?
So the question is this spacing arbitrary? Yeah, it's just what I chose. It just seems like plenty of space. You can condense this design quite a bit, but to make our life easy for a demonstration here, we'll just leave it as is.
Is there a way to use the cursor to measure from one point to another to see distances in units, like inches or centimeters or something?
So the question is there basically a ruler tool? And I think, yeah, there's a measurement. Is there a measurement or dimension? I think it's measurement. So you can select an XY distance or something like that, and click on the second point, and it gives you the distance down here. I can't.
In mils.
And this is all in mils. Yeah, all of your dimensions here are mils. So 1,000 is 1 inch. Yeah. So this is basically 1.5 inches. It's a pretty small board. Any other questions so far? Okay, so we're ready. When you want to move components around, and this was selected by default when we started, there's the component tool right here. So when you click on this, you can click on a component and drag things around. If you don't want to replace the component, you can just hit escape and it'll go back to where it was before. There are a lot of other tools up here. There's a pin tool where you can select an individual pin. Typically won't let you move it around because it's attached to a footprint, but it's useful if you want some information. So there's the tool to the left of the component, which is query, and it brings up basically a window, the query window. So if you have the query window open and the pin tool, for example, we can click on pin 5 here, and it'll tell you that it's on component J1. Here's the location of that pin. Here's the pad stack, so if you want to go and modify that pin size, the actual footprint for it. It'll tell you what pin on the actual device it is, what gate group. There's only one gate group on this. It'll tell you that it's not routed, basically. All of it's unrouted. It'll tell you what net it's connected to. So the query window can help you figure out kind of what's going on. You can use it with most of the different tools, including the component tool, and so on and so forth. There's an obstacle tool. So this is where you can draw your board outline. It's where you draw copper pores. It's where you can draw arbitrary artwork on the silk screens or copper, or the solder mask. So we'll use that tool later. There's a text tool, so if you want to put down in copper or in your silk screen or any of the layers, you can write text. There's a connection tool which will allow you to change net connections, and I highly recommend you stay away from this one. And there's an error tool. So when you run your design rule check, it'll pop up little error circles, and you can use the query window combined with the error tool, which we'll show you probably next class at this rate, and it'll actually show you what your design error is. We have color settings for all the different layers. The online DRC, which we've already seen, which is the square box in the center of your screen. There's a reconnect mode, which we're not going to deal with. And then there's a lot of things to actually do your routing. So refresh all is the same thing basically as F5. Design rule check will actually run a design rule check as opposed to the online DRC. Again, we'll show that next time around. Selection filter we typically don't use, but these are the big ones we're going to use. You can edit segments and you can add or edit routes. You'll find that these two behave slightly differently when you're pushing tracks around, but we're going to use these to actually begin routing. So to start off with, let's deal with some of our power. So power is going to be pretty easy for us to deal with. So for example, we have this capacitor right here, this C1 that's kind of buried, and it's going to these two pins. So that's a nice, simple, short, easy trace to route to start us off with. So we're going to click on the Add or Edit Route mode. And then you have to pay attention to what layer you're on. So we're going to stay on layer 1 because we're going to route this just on the top. And then you can click on a pad or an air wire, and you'll notice it begins drawing this green line. So the green line is the trace it's drawing. The yellow line is still the air wire. So you'll notice it's drawing at 45s. Oops. And one of the slash keys, and we'll deal with that later. If you right click, you can change 45-degree corners versus 90-degree corners. A lot of times 45s are useful to have. Snap to the grids. You also can unroute segments, so that's just basically the last little bit of trace you can rip up. You can unroute the whole net, which is that net everywhere on the board. You can unroute the whole thing back to the pin, and so on and so forth. Now you can exchange ends, so that's X. So let's see what that does. So now you'll notice we're coming out of the capacitor. If we just type X, which is the hotkey again, it now comes from the component. So sometimes it's useful to start from the opposite end of the trace when you're actually doing your routing. But we're going to start from the component. You can add vias by just typing V, and it'll drop a via right there. But also, you can add vias by just changing layers. So right now, let's say that we're on layer 1 top, and I'm just going to click and draw this trace out to here. So we now have traces going out to here. And if I type 2, or go to this menu and select bottom, it says the via will not be on grid, set via grid to 0. Yes, because sometimes it likes to keep vias on grids. For us, we don't care. So now you'll notice there's a little colored marker here. So that is a via. If I click again, I've now drawn a trace on the bottom layer. So we have this trace coming out of this pin into a via. The via goes down, and we pull out of that trace on the bottom layer. So this is how you transition between layers. Does this make sense? Now let's pretend like we have a trace that is in our way. So I'm going to keep routing. And let's pretend like this air wire is a trace. Now if I type 1, or go to the menu and select top again, it drops another via, and I can continue routing on the top layer. So this is a way that you can go under traces or around traces that are causing you problems. So remember, when you're doing board layout, think in 3 dimensions. Yeah? So the question is, if the via is plated all the way through, how do you keep from shorting ground and power? So the annular ring around it still stays put as is. But when it's not connected, there's basically a relief around that annular ring. When it is connected, there are those little thermal spokes going into the plane layer. So it does it automatically for you. Since this isn't ground and it's not power, when you place a via, it knows that those plane layers are ground and power, and it will not connect them. Correct, because we went into the nets and we selected that ground is tied to the ground layer. So at this point, we really don't like what's going on here, so we're just going to delete that whole segment because we want to stay on the top layer. So let's go ahead and route this trace. So again, we're in the Add Edit Route. We're going to click on the pad, and we can start drawing. So we don't want to have, if we exchange ends, if I route it like this, so I just click on where I want it to go, you'll notice that we're now kind of shorting out number 11. So that's a bad thing to do. So we'll click on this, hit D to delete it, and we'll route from this pad down, and you'll see we now have a connection between these two. A couple other hotkeys I want to mention. So we have these assembly top, the fab drawings, all these things that are kind of getting in our way, and they all look kind of green. So let's go to the fab drawing, and we now can go to View and say Visible or Invisible. The hotkey for this is the minus sign. So that means that that layer is going to disappear, and it's now in slash marks as opposed to solid color. You hit it again, it shows up again. So we're going to go to a couple of these layers we just really don't care about, like the assembly layer, and hit minus. Now everything disappeared. So the redraw on this program is terrible. So you can go back to the layer you care about, and it'll redraw everything back again. So now we don't have all this clutter on here, and you can see that clearly this trace is just a trace, and it's not running into anything else. So we can do the same over here for 12, and it's routed. Now you notice that these traces are really thin, and these are actually some power traces for this flyback capacitor. So we can click on the trace, type W, and that'll allow you to change the trace width. So let's set this trace width to something like 12. And now this segment that we draw will be 12 mils wide. And it'll say, well, it's still pretty small compared to the size of the pin and the pad. We can go bigger, so let's make it 20. At this point, you can see that the trace is still finer than the pad, so you're not going to be adding any risk of shorting. But that way we can actually have higher or thicker power traces, which has less resistance, which is better for your design. So thicker traces are better. Use thicker traces wherever you can. So we're going to just rip up this whole trace because it's very short. Hit W. We'll make it 20 as well. We don't want to go this direction for our routing because we're going to short with pin 11. So we can hit X to exchange ends, and that way we can begin routing down. Now unfortunately when I hit X, it forgot about the trace width. Again, it's wonderful software. You'll love using it. So we'll start routing from the right end, hit W, change the width, complete the segment, and we now have one component routed, this one capacitor. So now we're going to continue doing this for the rest of the components. Well, so we have this capacitor, which you can see goes to the power plane. So this is one of the bypass capacitors. So the proper direction of your current flow, actually this is not, sorry, this is a charge pump capacitor. Ignore what I said. So let's go ahead and just route this one because we're in the vicinity. So you can click on a pad, you can begin routing your trace. Now we're going to do something a little different. We're going to turn on the online DRC. So the window size can still have the whole pad and where we're going. Yeah?
Why is it rotated like that? It seems that if you rotate it 90 degrees, it'll be simpler to route. Is that true? Or?
So the question is, why is it rotated this way? It doesn't really matter. But yeah, you're right. If we want to, we can take this component and rotate it like that and probably be better off. Now you'll notice that I tried to place these components too close together and they're overlapping, so it gives you an error since we have online DRC. Which is also partially because it's not in our window. Okay, so at this point let's route pin 11. So I'm still in the component tool. So again, I'm moving this component and I really don't want to because you can see I'm screwing up all these traces already laid to C1. So just hit escape and it'll go back to where it was. So we got to go back to our add edit route mode. We'll click on this trace and begin routing. Now you'll notice it kind of gets stuck right here. I'm dragging and it's not running, and that's because it's doing that to actually satisfy the design rules. So I'll click here, and it's saying, you can't make it in between these capacitors unless you're right here. So you'll notice that it's red right now, which means that the only way I can get across is to drop layers. But if I get it just in the center, it turns green, which means I can fit in between. And if I go just one grid space further out, it won't fit again. So we're going to go in between the traces. So we've now wired up this one connection. Yeah, question?
When we drag the components around with the trace,
So if you drag components around, it'll drag the traces around, and in general it'll mess things up. So in general you don't want to drag components once you route them. Yeah?
Now, if you try to make the middle trace thicker, will you get an error?
Absolutely. So if we click on this trace, and you can see we're rerouting the segment. We type W and we make it 20. Now if I try and go across, it doesn't let you get it any larger. If you needed a thicker trace, you'd have to route it a different way, drop a via, something like that, and go to a different layer. Now this capacitor is basically a holding via pin 11 at some voltage. You can take a look at the schematic right now, and you'll see, so we're looking for C5, it's right here. You'll notice that this is the segment that we were just routing, so it highlights the segment as well. So it's kind of nice having some tool integration. And the other side of this basically is just going to power. So this is taking some really high voltage rail from the charge pump inside the line driver, and it's using this capacitor to hold it at a higher voltage. And so instead of putting this at ground, we reference it to the VCC rail, and that just makes the total voltage across the capacitor a little lower. It's a little easier on this capacitor. You don't have to have as high a voltage rated capacitor. So this other pin, we can just drop directly to the power plane. So if we zoom in right here, we can start routing this. Now it's red, but remember that this is just the air wire, and we wanted the air wire to be red so we know it's power. It's not red because it's on the bottom side of the board. Just like this one right here is not green because it's on the bottom side of the board. It's a green air wire indicating to us that it's ground. So to route this connection, again, we're in the Add Edit Route mode. We'll leave DRC on. We can click on this net, and you'll notice it's wanting us to route it to the pin on the chip, because this pin on the chip also goes to power. But these aren't really connected directly, right? It doesn't matter. We're not trying to connect this pin to this pin. We're trying to connect both of these to our power rail. You guys understand the difference between them? So remember that it's going to draw these air wires between everything that happens to be on the same net. So what we're going to do is we're just going to pull this trace out just a little bit, and we'll click. So we have a little piece of trace. And now we can drop to our power plane. Well, it's not letting us, so we'll just route a via. So if we add a via right here and hit escape, this via now goes to the power plane. So this trace right here is actually routed.
Did it go to the power because you had specified it was the power net?
Yes. So the via is connected to the power plane because we went to the net selection, we selected VCC, and we set the plane layer for VCC to be power. And
why didn't it let you automatically do that?
So why didn't it let me automatically do that? I have no idea. Now this is a weird color thing. Right now I selected layer 4, which is our power layer. And for some reason it shows up in red as opposed to green. Again, I have no idea. It's what an expensive piece of software does for you. But if you look at it right now, this via, let's hit F5 to redraw, we have no copper on the power plane. Remember that plane layers are negative planes, so we have no copper where this is red right now. So that means that this via is connected to the power plane through these spokes. And these spokes are the thermal relief. Again, it allows you to solder it. Not really necessary for vias, but I think it also makes their plating process probably easier. If we were, for example, to go look at some other via, so let's go back to our top layer, zoom out a little bit, and let's start routing this trace 7. So again, we're in Add Edit Route, we're on the top layer. We'll click on this pad and start routing out. So we'll go to here, and we'll hit V to add a via. And then we'll go to the bottom layer and we'll route somewhere over here, and we'll hit Escape. So we have a little piece of track here that's going nowhere, but we have a via. So if we go and look at our power plane again, you'll notice there's no ring around it. So you would think that no ring means it's connected. No ring actually means it's not connected. The partial ring means it is connected. Why? I don't know. That's just what the software does. So if you see this spoke pattern, then you know there's a connection between the via. If there's no pattern around it, then there's no connection to that plane layer.
So if we went to the bottom layer, we would see that?
So if you go to the bottom layer, you'll see your small annular ring right here. If you go to the top layer, you'll see the same size small annular ring. And if you go to your power or your ground layers, you'll see a larger ring right here. So this is the annular ring plus the spacing to make sure it's not connected to that layer. Now you'll notice over here, because we have ground selected, that this pin is already connected to the ground layer. So this is the ground of our power input. And pin 5, which is a ground on our D-sub connector, is also connected to the plane layer. So it's automatically connected these to ground. So that means you do not need to route this trace right here between C6 and that pin to get this capacitor grounded. So let's take a look at how you would do your proper power bypassing. So let's go to the top layer, because again, that's where we're just going to keep most of the traces for this design. We're going to turn off online DRC because we want to route a long distance. And we're going to connect pins 8 and 9, our power pins, properly. So beforehand, I'm just going to rip up. All right, so let's begin routing 9, which is our power. And we want our power to go from the pin to the capacitor, from the non-polarized capacitor to the polarized capacitor, and the polarized capacitor to the power plane. Now in this design, the power plane and this jumper are right next to each other, so we're just going to go into this jumper. You do not want this pin to go right here to this via and into the power plane, because then you have a current loop, and you're drawing current up through this via and into the pin. You want your current flow to be from the power source through the polarized capacitor, through the non-polarized capacitor, and then into your device. Now this may look like a huge distance. This is really small. This is, let's see, if we look at our y-coordinate here, this is 3/4 of an inch up, and this capacitor is 1/2 an inch up. So this is a 1/4 inch right here. So that's very close. That's sufficient. That's plenty sufficient for your bypass capacitors. You may want to put them over on the side, but that's going to clutter this design. So we'll again do the same thing for the ground, so that way our ground current path also goes through this capacitor. So we're already on the route mode, and we'll just click through, make things look pretty. And we're done. Now you'd probably want to make these traces wider, but for the sake of time, we're not going to. So you basically go through your whole board, routing all these traces. 1 second. So one other thing I just want to show you while we're looking at this is if you route something close but not quite, it may be hard to tell that it's not routed. And it's hard to tell what parts of this are not routed and which ones are, because sometimes this green blends in. So you can go to, let's see if it's even a menu option. High contrast. So the short key for this is period. And it basically grays out everything except your air nets. So if you look at this and zoom in, you can see very clearly that this isn't connected. Whereas if we hit period and we go back to normal view, it may not be quite as clear, especially if this trace was green. So the high contrast mode will definitely be helpful when you're trying to figure out what's connected and what's not. So a couple questions. Yeah?
When you connect the capacitor to the jumpers rather than the power plane by vias?
So why do I connect these capacitors to the jumper right here as opposed to the power plane? So this jumper is actually the power connection to this board. If we go back and look at the schematic, that's our input power. If we had this component somewhere further away on the board, if this was a larger design, you would go from here, from the pin to the non-polarized, to the polarized, and then to the plane. That's the proper way to do it. But again, this is kind of not really a 4-layer board. I mean, we're using 4 layers, so like this would be the example of taking a via to the power plane. So if it was a larger design, you definitely would do that. For this simplified case, we're just going to go straight in because it's right next to each other. Yeah?
Let's say we want to get all the thick traces at once. How do we change the default trace width?
All right, so the question is, if you want to make a bunch of traces thick, how do you change the default trace width? So again, that's under Tool, and then Net. And remember that your trace width is right here. So if we want to change our default trace width, let's just change it for ground, for example. We know we're going to have fat ground traces everywhere, and we're not going to need some high density. We can bump this up to 20. And now if we begin routing this ground trace, it's 20.
So that only changes the future traces, that doesn't change the ones.
Correct. Changing on the net widths on the spreadsheet only changes additions that you make. It does not go back and change traces you made before. Pad stacks are different. If you change the via inside of the pad stack menu, so again, if we go to Tool, Pad Stack, select from Spreadsheet, and we manipulate this pad stack for the via, all of the vias in your board are instantly changed. So pad stacks are instant, wire trace widths are not. Yeah? Say that again? So how do you get rid of this thing? Sometimes you can't. See if this works. Nope, it doesn't. Sometimes you're just stuck with them. You have to be careful. Usually these go away. I don't know why it's not right now. So if we go to auto refresh all, there we go. So if you go to auto and then the refresh menu, so minimize connections will change the air wire location. So remember, there may be a bunch of pins across your design that all have the same air wires connecting them. But if you drag a part somewhere far across your design, you may have one air wire that's, for example, ground. Instead of going to a ground capacitor right next to it, it may go all the way across your board. So if you go to minimize connections or just type M, it'll shorten all the air wires to the nearest neighbor that's on the same net. If you have some weird air wires that are left behind, for example, like after we drop that via, you can just go to auto refresh all, and that will take care of some of the leftover scraps. Yeah?
Is that the same as F9?
I do not believe that's the same as F5. I believe F5, no, redraw is home. It may be the same as F5. I'm not sure. Any other questions? Okay, so at this point, I'm just going to show you the design rule check real quick. Yeah.
Because you changed for the ground trace with only the default size, if you wanted to like place it through a part the way we did for, I don't know what.
Like right here?
It would draw it thick for where it could, and then it would make it small where it just.
Pretty much. Sometimes you have to change the widths by hand. So the question is, since we changed just the nominal trace width for ground and not the minimum, can we still do little tricks like this with our ground net? And you can. It won't necessarily automatically go from 20 to 8, then back to 20 or whatever it is you need. Sometimes it'll just stop there and force you to place a via unless you manually then type W, change your width, and then route one more segment. And then type W again, and then type 20 to make it bigger, and then continue routing. Yeah?
Isn't that a bad idea? Because it's not basically just like having a beat with.
So the question is, if we have something like this, if we made the part on either side of this component huge and just had some little tiny thing right here, doesn't that defeat the whole purpose? Why don't we make the whole thing 8? Well, so your total resistance, right, you can kind of think of it as an integral along the path, right? And if this is a fat trace in this area, you're going to have very low resistance over this distance. So your resistance across this path is going to be the resistivity, right, times the length, basically. So you're going to have low resistivity here, high resistivity here, low resistivity here. So if you integrate over that whole path, your total resistance is going to be less. Now, you still will have a bottleneck here, so to speak, of if you have a high current trace. So if you're worried about like burning a trace in your board, this little piece of trace that's small versus the big ones that you hypothetically would make on the sides could act like a fuse and burn up. But that's only when you're using really high current traces. If you're just trying to keep your voltage drop across these traces as low as you can, keeping it fat everywhere except for where you have to go smaller does actually help quite a bit. Yeah?
And how does that compare to if you just kept it fat and then went through a via like to the bottom?
So the question is, how does that compare if you just drop through a via? So that gets complicated. It depends on the wall thickness of your via as far as which one's better. In general, changing layers is a bad thing, and you want to minimize your vias over everything else. Sometimes you have to. Yeah?
What's the reason again we didn't connect C5's ground to pin 9? Is that obvious based on the schematic?
So the question is, why didn't we connect these two together? So pin 9 is the voltage source for this chip, right? Oops. Whereas pin 2 on C5 is just some voltage source that we're using just to keep this capacitor buffered. So we don't really want to be sucking power out of the chip to keep this capacitor charged. So if we go back to our schematic, you can see that pin 9 is our VCC, whereas pin 11 is this V plus buffer, right? So you don't really want to connect the capacitor between these two pins. You want to connect the capacitor between this pin and the power source. And then you want to connect this bypass capacitor between this pin and your power source, right? If we just drew this trace together, then potentially as you're drawing power from pin 11, it's going to be pulsing power out of pin 9. Whereas right now, the current draw for this capacitor is really going to be from your plane layer. And that pin 9 is going to be getting all of its power uninterrupted from this capacitor.
Which in turn gets it from the plane layer.
Which in turn gets it from the plane layer. The plane's kind of like your power reservoir, if you will. Yeah, last question.
So I was just wondering, how does it know that pin 9 is connected to your VCC? Or is that the net that is used before?
So the question is, how do you know that pin 9 is connected to VCC? Well, we connect it through these two capacitors and then into the VCC pin on here. So there is a connection between them.
How did it know?
How does it know that it's done that?
So how did it know? Why did it connect it to power off the
Oh, so it just, the layout program will automatically connect all of the nets together. So you'll have air wires between every point on the schematic that's VCC. So right now we have ground selected, so you can see all of these ground nets on our schematic that are all connected together. And the air wires are just arbitrarily drawn to the shortest distance. So if there are more questions, I'll take them right afterwards for just a few minutes. Otherwise, I think you guys have everything you need to start on your schematics and even begin layout. First thing on Tuesday, we'll cover how to make custom footprints for your components. And that will be the end. So Tuesday's our last class. So if you have questions, please feel free to email me. I'll be out of town until Monday night late, but I'll be available. So thanks a lot and have a good weekend.